Hello everyone. Last time we discussed about an flow measurement device which was called as the venturimeter. So today we will discuss another type of flow measuring device. It is called as the orifice meter. Alright. So venturimeter and orifice meter both are what? Obstruction type flow meters. Alright. So let's see the venturimeter. Sorry, orifice meter. Okay. So an orifice meter basically is used to measure the flow rate through pipes. Okay, flow rate through pipes. Now what does it have? Basically we have an orifice plate. Basically we have a plate, a metal plate. We cut that plate at the center, so we make an orifice at the center and put that plate inside the pipe, place it inside the pipe. So flow gets obstructed by this plate and it goes and it flows through the opening of the orifice plate. This is how the orifice meter looks like. Okay, so now what will happen? Now flow will get obstructed and because of the contraction it will be forced to pass through this opening. Okay, now according to Bernoulli's principle, what should happen? Now here the velocity will increase, alright, because flow rate is constant. Okay, so A1 V1 should be equal to A2 V2. Alright, so at this section, so we will use two sections here. Let us say this is section number 1. Okay, and this is section number 2. Okay, so at these two sections, this is number 1 and this is number 2. Okay, we will attach a differential U-tube manometer. Okay, we will attach a differential U-tube manometer. What should happen? Okay, what should happen when the flow takes place through this orifice meter? What should happen? The pressure should drop. Okay, so we are creating a pressure drop by installing a orifice plate. Okay, and once we measure the pressure drop using this differential manometer, we can get the equation for discharge like we did the last time. So we will do the same thing today just by applying Bernoulli's principle. So now here at section number 1, area is more, so of course its pressure will be more. Alright, but at this section, this is called as the vena contracta. Basically when the flow moves through a contraction, the minimum flow area is achieved at some point and then the flow will start expanding. Okay, so this particular section where the area is minimum is called as vena contracta. Okay, this section is called as vena contracta. I'll write it here. Minimum area section is called as vena contracta. Okay, so at this vena contracta, let's say area is AC and velocity is VC. Velocity at vena contracta, V equal to VC. Okay, now there is a relation between this vena contracta and this area of the orifice plate. Okay, area of orifice plate is, suppose if it is A2, then A2 and AC are related as AC will be equal to CC into A2. Okay, so CC is the coefficient of contraction. Okay, CC is the coefficient of contraction. So we can get the area of vena contracta by multiplying the area of contraction with the coefficient of contraction. So we will get the area of vena contracta. Okay, it is slightly less than the area of the opening here. Okay, it will be slightly less. Now see here, flow will separate. When the flow passes through an orifice meter, flow will separate here. Okay, so this flow separation will cause eddies, and this eddies, because of this eddies there is a higher loss of energy, and that's why the head loss across the orifice meter is very high. Okay, fine, that we will discuss later. Now first we will derive the equation for the discharge through this orifice meter. Now see, if you have a manometric liquid which is heavier than the pipe fluid, Okay, then what will happen? Pressure here is more, so it will press down the manometric liquid and you will get a difference like this. Okay, so you will get a difference like this. Last time also we saw, we will call this as X. Okay, X. Now if you apply Bernoulli's principle at between section 1 and 2, between at 1 and 2, section 1 and 2, what we can write? Z1 plus P1 by rho g plus V1 square by 2g, that should be equal to Z2 plus, now here P2 by rho g plus here in place of V2 square I can just write Vc square, because here we are measuring the our measurements are at location number 2, but here the velocity is at the velocity of the vena contracta, so Vc square upon 2g. Okay, so finally what we need is, we need this one, Z1 plus P1 by rho g minus Z2 plus P2 by rho g, that we need, because what is this? This is the piezometric head at section 1. Z1 plus P1 by rho g is the piezometric head at section 1, and Z2 plus P2 by rho g is the piezometric head at section number 2. So the difference will give, difference in the piezometric heads at 2 sections will give the velocity head. Okay, will give the difference of the velocity head. So Vc square by 2g minus V1 square by 2g. Okay, this is your h, we represent this by small h. Okay, this is our difference in the piezometric heads. Alright, this h equal to Vc square by 2g minus, now V1 square by 2g, I can write V1 in terms of Vc using the continuity equation. So continuity equation states that A1 V1 should be equal to AC into Vc. Okay, so entire flow is passing through this vena contracta, so area of vena contracta into velocity at vena contracta should give you the discharge. Okay, so A1 V1 should be equal to AC Vc, so you can write V1 equal to AC by A1 into Vc. But what is AC? Area of vena contracta. How you can replace that? Here we have seen that AC is equal to CC into A2. So just write CC A2 into A1 into Vc. Why we write in this way? Because see, A2 and A1 are quite measurable. A1 is what? Pi by 4 d1 square. A1 will be what? Pi by 4 d1 square. A2 will be for what? Pi by 4 d2 square. This diameter d2. Okay. This opening we can measure. Alright. So A1 and A2 we can know. So this is quite easy to calculate. Okay. That's why we represent area of vena contracta in terms of coefficient of contraction and area of opening. Alright. So now we'll just replace that here. We have CC square, then we have A2 square upon A1 square into Vc square by 2g. Okay, now let's take this Vc square by 2g common, and we have 1 minus Cc square A2 square by A1 square. Okay, so we can write, therefore we can write H is equal to Vc square upon 2g into A1 square minus Cc square A2 square upon A1 square. Okay, now let's calculate the value of Vc from here. Therefore we have Vc equal to, just take, it will be A1 upon under root of A1 square minus Cc square into A2 square into under root of 2gh. Okay, but what is discharge? See, discharge is Q is equal to area into velocity. So just multiply AC into Vc, you will get, now we already know the Vc, So just multiply it by AC. So you will get A1 AC upon under root of A1 square minus CC square into A2 square into under root of 2GH. But again this AC is difficult to calculate, so we can represent in terms of A2. Okay. Therefore Q is equal to CC A1 A2 upon root of A1 square minus CC square A2 square into under root of 2GH. Okay. So this is the formula for theoretical discharge. But what will be the actual discharge? Actual discharge would be what will be the actual discharge? See, now this equation, while writing this equation, we have not considered the drop in pressure or the energy loss. The energy loss because of the viscous dissipation. Okay, viscous dissipation also contributes to energy loss, which is reflected in form of the drop in the pressure head. So that drop is not accounted in this equation. So in order to account that, we multiply this discharge by a coefficient of velocity here. Okay. So therefore Q is equal to CV into CC into A1 A2 upon under root of A1 square minus CC square into A2 square into under root of 2GH. Okay. So the same formula I am multiplying by CV. CV is the coefficient of velocity, which will give you the corrected velocity. Alright, actual velocity. Now this CV into CC is called as the coefficient of discharge. CD will be CV into CC. Therefore, final equation for orifice meter becomes Q actual is equal to CD into A1 A2 upon under root of A1 square minus CC square into A2 square into under root 2GH. Okay. So this is the equation for a discharge passing through a orifice meter. Okay. Now see, the coefficient of discharge in case of an orifice meter, range of coefficient of discharge is less. Okay. In case of Venturi meter, the coefficient of discharge is almost about 0.95 to 0.99. So losses are very less. But for orifice meter, the losses are very high because of the pressure drop due to this viscous dissipation also, and pressure drop due to sudden expansion also. There is sudden contraction, sudden expansion. These losses are extra than the Venturi meter, which are not present in the Venturi meter. So coefficient of discharge is very less, almost 0.6. CD is in the range of 0.6. Okay, for orifice meter. So this is how you can use an orifice meter to calculate the discharge through the pipe. Alright. Now in order to determine the coefficient of discharge, we have to do the calibration. So how to calibrate a particular Venturi meter, orifice meter? First, to take an orifice meter, pass some flow through that discharge, and you measure that flow actually in some container. Okay, and then you calculate the discharge using this theoretical equation. Where is the theoretical equation? And then by comparing both, you will get the CD, value of CD. CD is very sensitive to flow Reynolds number because losses are directly depending upon the inertia Reynolds number. So CD will vary across the Reynolds number, but you can still get an average value of CD, which can be used for the practical applications. Alright, so this is all about the orifice meter. Now what should which instrument you can use basically? The question is which instrument is good or which you should use. Now that depends upon your requirement. Okay. So if you take a Like if you have a venturimeter, okay, the same pipe you can measure the flow discharge using a venturimeter. Okay, this is your venturimeter. Okay, this particular is a venturimeter. We have converging cone, throat and a diverging cone. Okay, and this is your orifice meter. Now the main difference between these two is in this, what is the space requirement? So space required for venturimeter is very high, since its length is also very high. Okay, so high, and this is very low because it occupies very less space and easy to install. So this is easy to install, but this is a little bit difficult to install. It will occupy more space. Okay, now about the losses, energy losses. Energy losses are very low in case of a venturimeter. Why? Because you have gradual contraction and you have then even more gradual expansion. So flow will not separate, and the energy losses will be only because of the some viscous dissipation, and that are very low. Okay, but in this case the energy losses are very high. Okay, energy losses are high. Why? Because there is a sudden contraction and sudden expansion. So flow will separate, and because of the eddies there will be a lot of losses, energy losses. Okay. Next, this basically venturimeters are used for flow measurement through large pipes. Okay, through large pipes, and here generally orifice meters are used for flow measurement through smaller pipes. Now this is quite qualitative, but still this is one of the differences. Alright, so this is all about the difference between orifice meter and venturimeter. So you know that because of these things, CD value is 0.95, almost 0.99, and here CD value is almost about around 0.6 or in that range. Okay, so this is all about orifice meter and venturimeter differences. Alright, thank you.